From the very first moment astronomers spotted the interstellar comet Atlas, they realized something unsettling. This was not just another icy visitor from the distant reaches of our own system, but a fragment of an alien planetary nursery, rushing past us once in all of cosmic history. Miss it now, and humanity may never again touch this exact mixture of ancient ice and starlight. Before we unseal that frozen message from another star, I want you to be part of this investigation. Tell us in the comments what you would ask a traveler like Atlas, and if you want to ride along with real discoveries instead of just movie special effects, consider subscribing. Your curiosity is what keeps this journey through deep space alive for all of us. Astronomers classify Atlas as the third confirmed interstellar object ever seen passing through our solar system, after the elongated mystery called Oumuamua and the dusty comet named Borisov. Each of these wanderers formed around a different star, in a different disk of gas and dust. Together, they are the first physical samples of truly alien planetary chemistry we have ever been able to study. The first red flag that Atlas was not born here came from its orbit. Most comets that belong to the Sun trace long, stretched ellipses, leaving and returning over thousands of years. Atlas, by contrast, follows an open hyperbolic curve, the kind of path that never closes. Once it swings past the Sun, it is gone, its trajectory bending but never looping back. Buried in that geometry is a story about speed and direction. Even when it was first recognized, Atlas was already racing through the outer solar system faster than almost any spacecraft humans have built. As it falls inward, the gravity of the Sun will sling it to still higher speeds before hurling it away again toward the constellation Lyra, never to be captured as a permanent member of our planetary family. That wild motion might sound scary, but this is not a disaster movie. Atlas never comes close enough to threaten Earth. At its nearest, it stays farther away than Mars orbits the Sun, a comfortable cosmic arm's length. For us, that distance is perfect, close enough that our telescopes can dissect its light in exquisite detail, yet distant enough that we can treat this as a pure scientific encounter. The discovery itself began quietly in early July of the year 2025, when the NASA-funded Atlas survey in the Chilean Andes was scanning for dangerous asteroids. One frame among thousands showed a faint, moving smear that did not match any known object. It was not dramatic, just a tiny, off-catalog glow that refused to sit still against the background stars. When researchers went digging through earlier images, they found that same ghostly point had been drifting across their cameras for weeks without anyone noticing. These so-called pre-recovery detections are like finding older security footage of an unknown visitor. Each extra sighting gave astronomers a better handle on the orbit, and with every refinement the case for an interstellar origin hardened. Another critical clue came from the direction of the orbit. The planets, and most homegrown comets, travel around the Sun in nearly the same flat, shared plane, like traffic circling a vast roundabout. Atlas cuts through the plane on a steep, almost upside-down angle and moves in the opposite direction, as if a car had suddenly shot straight across the lanes against the flow. To get an object onto such a path, something dramatic must have happened long ago around another star. Picture a newborn planetary system, with giant planets migrating, resonances shifting, and countless icy bodies jostling in the outskirts. One of those gravitational scuffles flings a comet outward with just enough velocity to escape the star entirely. Atlas is the survivor of one such violent eviction, now finally wandering through our field of view. By the time we noticed it, Atlas was already awake. In telescopic images it did not look like a bare, star-like point but like a true comet, with a hazy head and the beginning of a tail. That fuzzy glow is sunlight reflecting off dust and gas streaming out from a tiny nucleus of ice and rock, a core so small and far away that no telescope can resolve it directly as anything more than a dot. Even from those early observations, something about its chemistry seemed off compared with many familiar comets from our own distant reservoirs. Atlas appeared unusually rich in certain easily vaporized ices, especially carbon dioxide, while ordinary water seemed surprisingly muted. It was as if we had stumbled on a recipe written in the dialect of a different stellar neighborhood, shaped by different metallicity and radiation conditions. To move beyond first impressions, astronomers tracked how the brightness of Atlas changed minute by minute and night after night. When they stitched those measurements together, a repeating pattern emerged. The comet brightened and faded on a timescale of roughly 2/3 of an Earth day. That is the rotation period, the slow turning of its solid nucleus under the distant sun. Compared with some small comets that whirl so fast they flirt with centrifugal breakup, Atlas spins at a leisurely pace. That gentler rotation likely helps hold the fragile interior together as jets of gas erupt from sunlit patches. Instead of being torn apart by its own activity, the nucleus has time to flex, vent, and settle, surviving this one close brush with our star before heading back into interstellar night. When astronomers looked more closely at the light curve, they found not one but two similar peaks in each full rotation. That pattern hints at least two major active regions on the surface, perhaps irregular fields of exposed ice or clusters of vents. As Atlas turns, one region faces the sun and flares, then rotates away as the second region takes over, creating a double heartbeat in brightness from a body older than our entire solar system. On the scale of individual grains, the physics is even more delicate. Dust near the surface warms, releases trapped gas, and can be lofted away in time shorter than the full spin of the nucleus, allowing the active areas to respond quickly to changing sunlight. The result is a coma that is not just a static cloud but a self-adjusting envelope, constantly reshaped as Atlas plunges inward. And this is only the beginning of what our largest space telescopes are starting to reveal. When the Hubble Space Telescope turned its mirror toward Atlas, it was like bringing a telephoto lens to a fleeting crime scene in space. From far beyond the orbit of Jupiter, Hubble saw not just a dot, but a delicate structure, a bright central coma wrapped in a teardrop of dust, already stretched by sunlight and the faint push of the solar wind as this alien comet fell inward. In those early images, one feature especially caught astronomers off guard. A subtle plume of dust seemed to point toward the sun rather than away from it, forming what is called an anti-tail. It is an optical trick of geometry and grain size. Larger particles, less affected by radiation pressure, lag along the orbital plane and can appear to stream sunward when seen from the right angle. Atlas was already teaching us cometary physics in 3 dimensions. Yet when Hubble's instruments hunted for the familiar spectral fingerprints of glowing gas, they found almost nothing. No clear signs of common cometary fragments like cyanogen or simple carbon chains, only a reddish continuum from sunlight reflecting off dust flavored with complex organics. That absence of gas lines, combined with the brightness of the dust, let astronomers place an upper limit on the size of the hidden nucleus without ever seeing its shape. Months later, Hubble looked again, this time as Atlas swept much closer to the sun. The coma had brightened, the tail had grown longer and more structured, and the comet's apparent motion against the stars had become so rapid that background sources stretched into streaks in the images. Each frame captured not only the comet itself, but the raw sense of speed as this interstellar visitor tore past the slow, fixed tapestry of the galaxy. Still, even Hubble could not answer the deepest question: what exactly are the ices and dust grains in that fuzzy envelope made of? For that, astronomers turned to a different machine entirely, a telescope that does not see invisible light at all, but in the glowing warmth of the infrared. The James Webb Space Telescope, hanging far from Earth, became humanity's spectroscopic microscope on this fragment of another world. In early August of the same year, Webb aimed its near-infrared spectrograph at Atlas while the comet was still well beyond the orbit of Mars. Instead of taking a simple image, Webb sliced the light into thousands of colors at once, building a three-dimensional data cube where every pixel in the coma carried a full spectrum. Hidden inside those spectra were sharp dips and peaks, each corresponding to a particular molecule vibrating in the cold vacuum. The result was startling. The coma of Atlas turned out to be dominated by carbon dioxide, with water playing a surprisingly minor role. Compared with typical comets from our own reservoirs, the ratio of carbon dioxide to water was dozens of times higher, pushing the object to an extreme end of known cometary chemistry. It was as if someone had turned the usual recipe upside down, with carbon dioxide promoted from a trace ingredient to the main component. Water was still there, along with a significant amount of carbon monoxide and hints of more complex sulfur-bearing molecules like carbonyl sulfide. Webb also saw signatures of solid water ice and a warm dust continuum with a reddened slope, consistent with grains coated in organic material. Put together, these diagnostics painted a portrait of a body that formed under conditions very different from those in the nursery of our own planets. At the same time, the data told a story about time itself. An object wandering for billions of years between stars is bathed in a constant drizzle of galactic cosmic rays, high-energy particles that can rearrange atoms in icy mantles. Over eons, that radiation can gradually convert mixtures of water and carbon-bearing species into more stable molecules like carbon dioxide, while burying complex organics under a processed skin. Atlas may carry such a radiation crust as a visible scar of its long exile that raises a provocative question. How much of the strange chemistry we see is baked in from the original birth environment, and how much is sculpted by the slow, relentless work of cosmic rays? If Atlas was born in a low metallicity region of the galaxy during a furious era of star formation, then it may have started out with fewer heavy elements and a different balance of volatiles. The comet becomes a time capsule not only in space, but in galactic history. Webb's spectra did not reveal obvious biosignatures or anything that could reasonably be called a direct sign of life. The molecules seen so far can all be produced by non-biological chemistry. Yet the combination of abundant carbon dioxide, organics, and the possible presence of sulfur compounds touches on themes that astrobiologists care about deeply. It shows that rich, reactive chemistry can arise even in planetary systems very different from our own. While Webb and Hubble dissected the light from afar, a whole fleet of other observatories joined in. A space telescope designed to hunt exoplanets, TESS, contributed precise time series photometry that helped refine the rotation period of the nucleus. Ground-based surveys like the Atlas Network and the Zwicky Transient Facility tracked the comet's changing brightness and tail structure over many months, building a continuous movie of its evolution. High-powered observatories such as Keck and Soar added detailed spectra at visible wavelengths, confirming the dominance of dust-reflected light and the weakness of certain gas emissions. From ultraviolet to radio bands, each wavelength region told a slightly different version of the same story. The interstellar comet Atlas was not a single object, but a multi-instrument collaboration stretching across the full architecture of modern astronomy. Then came perspectives from places no human has ever stood. Spacecraft orbiting Mars, including orbiters and a rover on the surface, turned their cameras toward the visitor as it passed relatively nearby to the red planet. Against the Martian sky, Atlas appeared as a delicate smear, its faint coma barely above the background noise, but its extended tail tracing the direction of the solar wind far out along the ecliptic. Farther out, missions like Lucy and Psyche, each with their own primary asteroidal targets, used spare time to image the comet from vantage points scattered around the solar system. Their long baseline views, combined with ground-based tracking, allowed scientists to reconstruct the three-dimensional structure of the dust tail, revealing layers and striations shaped by varying grain sizes and ejection speeds. Even solar observatories built to watch coronal mass ejections, like SOHO and Stereo, caught glimpses of Atlas as it swept through the inner system. Coronagraphs that normally block out the sun to reveal its atmosphere now doubled as wide-field comet cameras, recording how the interstellar tail responded to changing solar activity. Flickers and kinks in the dust and gas traced invisible gusts in the solar wind. The European mission JUICE also added its eyes, observing from the outer reaches as it made its own journey toward the Jovian system. Together, these disparate data sets formed a kind of cosmic triangulation. From Earth orbit, from Mars orbit, from interplanetary crews, and from deep space telescopes, humanity surrounded this single comet with instruments, refusing to let its secrets slip away easily. Yet, for all this coordination, one thing was missing: a close flyby. No spacecraft had been built or positioned with Atlas in mind, and its discovery came too late to organize a dedicated chase. That fact stings a little for mission planners, because a nearby encounter could have resolved the nucleus directly and sampled the dust environment with in situ instruments. Once again, as with Oumuamua, we are forced to learn at a distance. Still, dynamicists have noticed that as the comet's enormous tail stretches across the inner solar system, there is a chance that future spacecraft, including missions bound for icy moons and asteroids, may pass through its outer debris. If that happens, even a brief crossing could provide precious information about particle densities and compositions. The idea that a probe meant for one target might accidentally skim the breath of an interstellar comet adds one more layer of intrigue to this story. For theorists, Atlas is more than a pretty sky event. It is a test of our models for how planetary systems are born and die. By tracing its incoming speed and direction, they link it to the thick disk of our galaxy, a population of older, lower metallicity stars formed during a frantic era of star birth sometimes called the cosmic noon, when the Milky Way was young and restless. If that connection holds, then Atlas is not just from another system, but from another epoch. It may have frozen its ices at a time when heavy elements were rarer, ultraviolet radiation fiercer, and giant planets were carving paths through raw, unsettled disks. Its chemistry becomes a fossil record of that environment, a way to sample the conditions under which some of the earliest rocky worlds may have formed. The extreme carbon dioxide enrichment hints at a surface that has been patiently rewritten by galactic radiation over billions of years. Imagine layers of ice slowly darkening, water breaking apart, new molecules assembling in place. No biology is required to drive this, only time, energy, and the stubborn tendency of atoms to explore every possible configuration. Yet the end result is a cocktail of volatiles and organics that overlaps with the raw materials chemistry cares about for life. This is where speculation creeps in, carefully. No one claims Atlas carries life, or even direct biosignatures. But objects like this show that rich, complex chemistry is not a rare privilege of our own backyard. If icy bodies around distant stars can brew abundant carbon dioxide, organics, and exotic sulfides, then the menu of possible starting conditions for life across the galaxy is wider than the limited sample of our local comets once implied. The more we compare interstellar visitors with homegrown comets, the more diversity we find. Some are dust-rich, some gas-bright, some strangely quiet in familiar emission lines. Each one nudges us away from the comforting idea that there is a single, universal template for planetary systems. Instead, the universe seems to prefer variation, running the experiment of world building over and over with slightly different starting recipes. There is also a humbling lesson in logistics. Atlas arrived without warning on human timescales. Our instruments rallied impressively, but we still lacked a dedicated probe ready to pounce. That gap is pushing space agencies and private teams to think about rapid response missions, craft that could wait in cold storage and sprint toward the next interstellar trespasser when the alert comes. The cosmos will not schedule appointments for us. On a deeper level, these fleeting encounters force us to confront how small our observational window really is. For billions of years, comets like Atlas have been passing through the solar system, unseen, unmeasured, leaving only faint dust trails in the dark. We happen to appear at a moment when our technology is just barely good enough to notice. How many strange chemistries have already slipped past while we were not looking up? And yet, there is something profoundly hopeful in this, too. In a thin layer on one small planet, a species has learned enough physics to recognize when a grain of another world is flying by at fantastic speed, to decode its light into molecules and histories, and to argue late into the night about what those histories mean. In the grand timeline of the galaxy, we are only just learning to read. One day, perhaps, we will not have to study such visitors at a distance. Fast intercept missions or even autonomous probes built to live in deep space could meet an interstellar comet upstream, sniff its gases, taste its dust, map its nucleus up close. For now, Atlas reminds us that even with only light and patience, we can already glimpse across the boundaries between stars. The first steps of any journey are usually the most awkward. As Atlas fades into the background and its tail thins into invisibility, the data it left behind will continue to glow on hard drives and in minds. Years from now, new models of planet formation, new ideas about radiation chemistry, even new concepts for missions may trace their ancestry back to this brief passage. The comet moves on, but the questions it sparked stay with us, sharpening our curiosity. So when you hear that an interstellar comet is visiting, it is not just another headline. It is the universe knocking on our door with a piece of its wider story. We can choose to ignore it, let it blur into the constant noise, or we can lean in and listen, even if the message is fragmented and incomplete. Atlas is a reminder that the galaxy is not an abstract backdrop, but a living, dynamic place that sometimes sends samples our way. Now I want to turn this back to you. If you could ask Atlas one question about the place it came from, what would it be? Do you think objects like this make life elsewhere in the galaxy feel more likely, or do they mostly remind you how vast and indifferent space can be? Share your thoughts in the comments, and if you want to keep meeting these rare visitors together, join us here for the next one. After all, the cosmos will keep sending stories. Our job is to notice.